Hey everyone, welcome back to the show. Michael, how are you doing today?
I'm doing fantastic. Really thrilled to be here.
So, when we talk about chemical bonds, what are we really diving into?
It's basically how atoms connect, how they achieve stability by joining up.
Stability, so they're not happy alone.
Not usually. They're looking to fill their outer electron shells. And a fantastic way to see this is with Lewis dot structures.
Lewis dots, what are those?
They're super simple diagrams showing only an atom's valence electrons. Those are the ones on the outermost shell.
Oh, so the ones that actually do the bonding.
Exactly. They're key to understanding how bonds form, and one of the most fundamental types is the ionic bond.
Ionic bonds, is that where electrons are shared?
No, that's the other one. Ionic is when one atom completely transfers its electrons to another.
Wait, so not sharing at all.
Nope, a complete handover. Think of it like a trade. One gives, one takes.
And then they become charged.
Precisely, creating ions. A positively charged one and a negatively charged one.
So they stick together because of those opposite charges.
You got it, like tiny magnets. That strong electrostatic attraction is the ionic bond.
And you can visualize that electron transfer with the Lewis dots.
Absolutely. You literally see the dots move from one atom to another.
So, we're talking about how atoms stick together. How do we even begin to visualize that connection?
That's exactly where Lewis dot structures come in. They're visual shortcuts to see an atom's bonding behavior.
Visual shortcuts, like little drawings.
Exactly. You use dots to represent the atom's valence electrons, those outermost electrons that do all the work.
Only the outer ones.
Just the outer ones. Those are the key players in chemical reactions.
Okay, so dots for valence electrons. And why do we care about where those dots are?
Because atoms want to be stable. They're usually trying to get 8 valence electrons around them.
The famous octet rule.
You got it. And Lewis structures beautifully show how they achieve that, whether by sharing electrons in covalent bonds.
Or something else. What about ionic bonds?
Oh, Lewis structures are perfect for ionic bonds. Instead of sharing, you literally draw the electrons transferring.
So one atom gives its electron dots away completely to another.
Yes, you see the electron move, and then the atoms end up with a full octet and opposing charges.
And that's what holds them together.
Precisely, the attraction between those oppositely charged ions. Lewis structures make it super clear.
So how do we figure out the best structure for a molecule, the most stable one?
That's where formal charge comes in. It's like a bookkeeping tool for electrons within a Lewis dot structure.
Bookkeeping, what does that even mean?
We calculate it for each atom. It's the atom's valence electrons, minus its non-bonding electrons, minus half of the bonding electrons.
Wow, that's a formula. So what's the goal with this calculation?
We want formal charges as close to zero as possible on every atom. That tells us we've found the most stable Lewis structure.
So if you have multiple possible Lewis dot structures, you just pick the one with charges closest to zero.
Precisely. And if there are negative charges, they should always be on the more electronegative atoms.
Okay, so it helps us visualize electron distribution. But how does this relate to an ionic bond where charges are explicit?
Great question. Formal charge isn't a real charge like in an ionic bond, where electrons are fully transferred.
It's more of a theoretical assignment then.
Exactly. It helps us compare different covalent structures, not define full ion formation. It just indicates electron favoritism.
So it's about minimizing electron imbalance within a shared system, not a complete transfer like an ionic bond.
You got it. It's a way to find the most representative Lewis dot structure for a molecule.
So ionic bonding, what's the big idea behind it?
It's pure electron transfer. Giving and taking, no sharing here.
Who gives what to whom?
Metals are the generous givers. Non-metals are the eager takers.
Why do they do that?
To get a super stable, full outer electron shell.
Oh, like with Lewis dot structures.
Precisely. Those dots show their valence electrons. Metals want to lose them.
And nonmetals want to gain them.
Exactly. Think sodium 1 dot, chlorine 7 dots.
So sodium just hands its one dot to chlorine.
Spot on. Sodium becomes positive, a cation.
And chlorine.
Becomes negative, an anion.
And positive plus negative.
Creates this incredibly strong electrostatic attraction. That's the ionic bond.
So metals and nonmetals transferring electrons completely.
Visualize it with the Lewis dots, and you've got ionic bonding down.
So we've talked about how ions form, but what actually makes these ionic compounds so incredibly stable?
That's where lattice energy comes in. It's basically the super glue of ionic structures.
Super glue, so it holds them together really tightly.
Exactly. After atoms trade electrons to form those ionic bonds, like we see with Lewis dot structures.
Oh, so like sodium giving an electron to chlorine, right?
Yes, those Lewis dots show the transfer. Then, the newly formed positive and negative ions snap together.
And that snap is the lattice energy.
That pull, yes. It's the energy released when those oppositely charged ions form a crystal lattice. The stronger the pull, the more stable the compound.
So what makes that pull stronger?
Two main things: the charges of the ions and their size. Higher charges mean a stronger attraction.
So if you have a +2 and a -2, that's stronger than +1 and -1.
Much stronger. And smaller ions can pack closer together, which also boosts the lattice energy.
So smaller, more charged ions mean super strong bonds.
Precisely. It makes them really difficult to break apart.
So wrapping things up, what are the absolute key takeaways from our chat today?
For sure, Lewis structures are fundamental. They show us how electrons arrange around atoms.
Like a visual map.
Precisely. They're our blueprint for understanding how bonds form. And don't forget, formal charge helps us find the most stable structure.
That's right, to make sure the map is.
The best, most accurate map. And then, ionic bonding. That's all about total electron transfer.
So one atom completely gives away its electron.
To another, think of it as a complete exchange, creating charged particles,
Positives and negatives.
attracting strongly, metals giving to non-metals. It's what gives them unique properties.
So understanding those structures, the stability with formal charge, and the electron handoff.
It really unlocks so much about how matter behaves. It's the core.
Well, that really ties it all together.
Yeah, it does.
Thanks, Michael.
Thanks for having me.